everyone. In this video, we're going to go through the solution guide for the Maths Method SAC number 1. Just a few things you need to remember when going through the solutions is the main one is that your SAC, so what you wrote in your SAC, didn't have to be exactly the same as what I've written in my solution guide. In fact, you had 4 hours, and I would say this solution guide, actually I have no idea how long it took me to do because I did it whenever I had some free time to work on it. But to get full marks, you didn't have to write exactly everything that I've got in this SAC. Okay, so I basically, when I was doing the solutions, thought, okay, what could students write about? And I put that in, all right, because I wanted to make sure that I had something written for whatever a student could write, just so I didn't have to keep thinking about it on the spot. I had a quick reference. Now, having said that, some students wrote stuff that I don't have in my solution guide, and I was like, oh, this is awesome. I was really pleased to see that. It kind of showed that you went away and thought about something a little bit more. Maybe you already knew about it, don't know. But I could definitely tell that students went away and thought about the prompts, which was really good. Another thing is my solutions, in some parts, I didn't go into too much detail because there's 28 of you, and if if I was to give an example or give every possible example, it would be a very long solution guide. And in some parts, I just knew, okay, for this section, here's a definition, but I would also expect a student to show me an example or a diagram to support their response. And I might not have done that in the solution guide. So just keep that in your mind as well. With this solution guide, think of it as being given a sample essay response in English. So in English, you would have an essay topic, and if all 28 of you responded to that essay topic, you would have 28 different essays. So I had 28 different SACs to mark. And in marking them, I had to differentiate between who gave a really super duper response. All right, and that person would get full marks. All right, so it's hitting basically the things I've got in the solution guide, but there's a bit of clarity in there. There's confidence with what they've done. It's just not maybe regurgitating definitions that they've found. Like I could clearly see that they understood what they were talking about. They gave examples to support what they were saying, or gave diagrams. I'm just trying to think of what the top students did. It was a while ago since I've marked these, but yeah, basically, in their discussions, it was quite clear what they were talking about. So in an English essay, that confidence in responding to the essay topic, I was kind of looking for that confidence in responding to the sections in this SAC. So if I was to give you the SAC from the student who got the highest result, you could probably see how much better that was than someone who got fewer marks. So what level of detail they went in, how clear it was in their response. There were very few errors. So sometimes errors would pop up and it was like, well, that indicates to me some confusion in what you're writing. And some students were able, as I said before, were able to put in things that showed an understanding of a concept, which I didn't really touch on in the solution guide and wasn't really touched on in depth in class either. So an example of that was, which I really liked to see, which I liked seeing when I was marking, was with tan graphs and asymptotes. And students talking about, well, an asymptote exists when cos is equal to 0, because tan is equal to sine over cos, and if cos is equal to 0, then you've got an asymptote. And I was like, that's great, showing or explaining why a tan graph has an asymptote. Anyway, 5 minutes of rambling. Let's get started. So as I said before, I'm not going to go through every solution. I'm going to talk about what was done well and what wasn't done as well. And hopefully that gives you a better idea of what was expected. All right. So again, I gave a lot more detail. So you can see in part or question A here, I've given the domain and range of all the functions. You only had to do 2. All right, so talking about, when you're giving definitions, an example is fantastic. So if you were talking about implied domain or implied range, then giving an example was what I wanted to see. And if you gave a graph to support that as well, that was fantastic. Talking about one-to-one functions, was good, and giving examples, and I wrote in the SAC the definition of one to many, and I meant many to one. So I was a little bit flexible here. If you gave the definition for many to one for one to many, that was fine. I still marked that correct. And if you gave the definition for many to one and one to many, I thought that was fantastic. So that was great to see. But obviously I didn't expect you to have both of them. So there was a bit of allowance there for the fact that I did mean to put one to many. But I did mean to put many to one. But students still gave the definition for one to many, because that's what it said. But some also gave the definition for many to one. Anyway, so just making it clear, I didn't expect both, but I have written both here because I think it's good to kind of clear up the distinction between the two of them. So many to one functions, so you can see there with your x squared, so your parabola, your truncus, your quartic graph, and doing the horizontal line test. So if you made reference to a horizontal line test, that was fantastic. If you talked about one to many, so a one to many is not actually a function, it's a relation. But you talked about the vertical line test, that was great. And when restricting the domain of a many to one function to make it one to one, and when you would do it, so that was done really well. But yeah, you can see there I've just gone on and done the definition for one to many as well as many to one. All right, so one to many, so one x value to many y values, so it is not a function, it is a relation. And you can't, well, it depends on what what the relation is as to whether you can actually restrict the domain or not. So as you can see what the example I've got on the screen, I couldn't restrict the domain because that's going to still make it one to many. You could restrict the range, but because the range depends on the domain, it's a little bit tricky. So I've explained that there. All right, moving along. All right, composite functions. So here I've written just the definitions for when it's defined and not defined, but having an example there to support it, I was looking for that. So using those functions in section 1 to explain what would be defined and what is not defined, and then having a clear example of restricting the domain so that the range is then restricted. So that was done really well. I was really pleased to see students explain that, because composite functions is always on the exam. So having a good in-depth understanding of composite functions is extremely important. And then, I keep talking. And then inverse functions, that was done quite well. Some of you gave an example of an inverse, which was great. I kind of did want to see an inverse example. However, if you just wrote it down and your working out was similar to what you would do if you were just doing a question from a textbook instead of actually explaining it. It was a little bit like puzzling why you would do that, because you should be right in when you're explaining something, you should be explaining it in a way that the person reading it knows nothing about, inverse functions. So you've got to explain it to kind of teach them. So if you're just doing a whole lot of maths without explaining what is happening, you're not really explaining yourself clearly enough. So that was one thing that when there were examples of working done, sometimes, there was just working without really any context or explanation as to what was happening. So yes, full marks weren't really given for an example like that. All right. Section 2 talked about transformations. So just discussing the different types of transformations. Again, to get full marks, would love to have seen examples. You can see there I've got dilations, but if you gave an example where you could clearly see that coordinate change, much better than someone who didn't do it, like I haven't done it here. Or explaining what happens, so you can see my different explanations there. So what have we got now? Reflections. All right, so you can see I've got example there where the points have changed. Translations. So this was all done quite well, which was good to see. And students did give graphs as examples, which I was very pleased to see. Just trying to think. All right, so order of transformations. This is something I wanted to raise because there were a few students who said they must be, so I think the prompt was, why is it important? Why is the order important? And students who said they must be done in the order dilations, dilations, reflections, and translations. When you said they must be done, that's not true. So I think you're getting confused with consistency. So if we're looking at a function written in, let me just go down here. So see this square root graph that I've got on the screen. So y equals 2 times the square root of negative x plus 2 and then plus 1. So when it's in a certain format like that, that is when you would follow the order of transformations, dilations, reflections, then translations. But you don't have to go in that order if your function was written a different way. Or if you're being told a bunch of transformations, they don't have to tell you in the order DRT. All right, you might be told the translation first and then the reflection, then the dilation. So with my example here, and it was really good to see students who gave an example, if you've had a translation and then a reflection, it's different to if you had a reflection and then a translation. So showing that distinction was really important. So an analogy that I could use is if I was going from Kilbreda into the city, there is more than one way of doing that. All right, I could go down Nepean Highway, I could go down Beach Road, I could go onto CityLink. There's not just one way. So when you're thinking about transformations, there's not just one way, and that one way is not just dilations, reflections, and translations. The DRT phrase, or whatever you want to call it, is only for when you're interpreting by looking at your transformations. All right, so just like this one here, when you're reading your transformations from a function, then you would follow DRT. But you don't always have to. You can go other ways. All right, so doing the mapping, again, giving an example and then function notation. Doggy's barking. Function notation was done quite well. It was good to see. All right, moving on to question 3 or section 3. So looking at exponentials and logs. Now this part was done really well. I was quite pleased with. Some of you, I just might write on here actually. Just with the value of A in the first one. Oh God, didn't mean to do that. I meant to highlight it and I just kind of crossed it out, didn't I? All right, so with A is your base. All right, A is the base. So some students would say there was a reflection along the x-axis. So if we've got an exponential graph, so here it is. All right, you can have, so that's exponential growth. And then you've got exponential decay. All right, so you can see basically it's been reflected in the y-axis. If A is less than 0, all right, that is not a reflection in the x-axis because A cannot be less than 0. A has to be positive. All right, it is a base. So don't confuse. So if I had negative 2 to the power of x, that is not the same as negative 2 to the power of x. All right, so effectively what I've got here is negative 1 times 2 to the power of x. And this negative 1 is our reflection. Because if I had negative 2 to the power of x, and x can be any real value, so let's say to a half, that is the same as the square root of negative 2. All right, and you can't get a real solution. So I just wanted to make that distinction because some students did talk about A being negative, but A actually can't be negative, it has to be positive. And I explain that in my solutions as well. All right, I just want to delete all this because I haven't actually written much on here. All right, I'm just trying to think what else was done well in here. So the explanations were really good for this. Logs were definitely done better than the exponential. So talking about asymptotes and the x and y intercepts, so that was done well. Yeah, some explanations of why there's an asymptote or why there was an x-intercept or a y-intercept didn't really kind of follow the understanding or the definition of an asymptote. So basically an asymptote is there because your function or f of x goes very close to that value but never touches it. All right, so for this one, for your exponential, that's our log. Let's go back to our exponential. Did I draw a graph? All right, let's do our log. So for our log, we have a vertical asymptote at x equals 0. And that's because your log can never equal 0 and x can never equal 0 because what we have here is a to the power of what is equal to 0. All right, so that's why we can't have it equal 0. And some students wrote that, which was really good to see. And then also talking about your asymptotes can change. So even though we didn't talk about transformations, it was really good to see if students said, oh, your asymptote can go left or right, if it's a vertical asymptote, or up and down if it's a horizontal asymptote. What was part 3C? Just trying to think. Oh, transformations. So some people talked about transformations, but not all the transformations. Okay, so when you're talking about transformations, you've got to cover them all. All right, and that's what I've done there. Hopefully they're all correct. It's been a while since I did these solutions, and I haven't actually gone back and checked them or changed them as I should have done. All right, and then the inverse. So that was done quite well. And some people had a graph to show them that they were the inverse. Talked about being reflected along the line y equals x. Yeah, I was quite pleased with that part. All right, let's move on. All right, section 4. So we're looking at circular functions now. I'm not sure whether it was just a matter of running out of time for this, but some parts were quite rushed. So I think the first part talked about these triangles. Oh, sorry, I just had a bit of a cough. Some students just put these triangles down but didn't actually explain how you use them to get exact values. So I kind of required that. And if you gave an example, that was great. Yeah, so it kind of goes to show the difference between getting full marks and not getting full marks. So if you just put the triangles down and didn't do anything with them, that kind of wasn't really what I was after. I needed you to show, well, if we're talking about the trig ratio, SOHCAHTOA, that's how we use these triangles. And I've put the exact values there so you can see how they work. Talking about the unit circle and symmetry, yeah, it was done quite well. And then talking about the graphs, I think. So how the quadrants, I was really impressed if students talked about the quadrants and the graphs, where it's positive and where it's negative. Again, drawing the graphs correctly was important. All right, just trying to think what this was. Oh, sine and cos graphs. It's talking about solutions. So some people said the solutions were the x-axis. Not necessarily, but I kind of didn't penalize you too much for that one. So you can see here we've got sine x equals a half. So basically that's just looking at where the graph intersects that line. Y equals a half. So you can see all those solutions there. So when you talked about this one, seeing a graph was extremely important to show, because I mean that's what it was talking about, using a graph to show the solutions. If you did say where it crosses the x-intercept, but yeah, I didn't really penalize you too much, but just remember that that's not necessarily true. It's only if it was equal to 0. Talked about that, yeah, blah, blah, blah. All right, talking about solutions was really good. And so this is, I guess there's multiple ways of finding solutions. So this was just one way. I didn't want to just put the one way. And then you could use your general solutions, which was also fine. And then part C, talking about the general solution. So what I've got there in pink, if you just wrote that, then, or the equivalent of, then I didn't give you full marks because you could have just copied that straight from the textbook or from your bound book. But actually talking about how the general solution comes about. So that was important to see. And then in 4C, talking about sine graphs and cosine graphs and the transformations. So just like with the exponential and log functions, if you didn't talk about every transformation possible, you kind of lost marks. Some of you just talked about the range being -1 to 1. Just trying to think what else, which it isn't. The range does depend on the amplitude and any translations. And then, all right, sorry, I've got a cough. And then talking about tan graphs, so, oh, nearly at the end. Sorry, guys. I had a bit of a cough. All right, so with your tan graphs, I'm talking about the transformations, the period, domain and range, and making sure you got your asymptotes correct. And by this point, I was a little bit slack with what I was doing. So just showing a sine graph, cosine graph, and a tan graph as well. All right, I'm going to leave it there because I'm not going to stop coughing. But, okay, I'll start again. I'm going to stop there. So please go through the solution guide if you haven't already done so. I'm more than happy to sit down with you and go through your SAC if you're still keen to know where you lost marks, etc. All right, thank you. Bye.